Okay. So what I would like to do now is talk a little bit about how we can benefit from increased soil carbon. And this is about a 10-minute presentation on about a 10-year topic. So it'll go pretty fast, and I'll try to cover everything in extremely shallow detail, but it should open up the opportunity for lots of questions. I want to cover some basic soil carbon principles, and Sierra and Lauren did a really nice job with this, but I want to revisit those principles from the standpoint of a market. Also want to add some rangeland management context in there, and talk a little bit about soil carbon as an ecosystem service in that management framework. I want to start with this one. Lauren had a nice figure on this one, but in particular, I want to focus on two things. Okay, I want to start with this figure. And in particular, I want to start with CO2 uptake via photosynthesis, translocation from leaves to roots, death, all that sort of stuff. That's how carbon gets in the soil. And I also want to focus on respiration. And not to go into great detail on this one, but these are the two things that we really need to know and really need to understand about how carbon sequestration works. And the best way I got a couple of analogies, the best way I can think of it to communicate it to you is if you took biochemistry in college, you spent one lecture on photosynthesis, and you spent 3 weeks on respiration. And that gives you an idea of the relative importance of these factors, of these processes, to carbon sequestration and to governing how much is sequestered. Another analogy for those of you who didn't take biochemistry, or for those of us like me who did poorly in it, think of CO2 and photosynthesis as putting feed over the fence, and think of respiration as Shetland ponies. It doesn't matter how much you put over the fence, they're going to eat it. So that's why in many cases we often put a lot of growth into plants, but we seem to lose that through respiration. This is the process that is all based on. And this also will give you an idea about why clay content of soil is so important. Clay particles or clay platelets are the smallest soil particles, and those are the soils that really do the best job of holding on to that organic matter, which eventually becomes carbon. So we start out, and these are in increasing order from the lower left-hand corner there, increasing order of a factor of 10. We start out with the small clay platelets. The bacterial debris starts to build up around those. Eventually that forms into very, very small aggregates that contain those clay platelets, the bacterial debris around them, the hyphae or root, very fine roots that grow into those. And all of that material gets kind of cemented into those aggregates. And then those aggregates start to form around the roots and eventually form what are about 2 millimeter crumbs. And a 2 millimeter crumb is about the size of, about the thickness of a nickel. You want to think about that. So we're dealing with some things that are fairly small. Now, some basic principles of those grassland carbon fluxes. Growth is input. Growth in rangeland situations especially is controlled by precipitation and inherent soil fertility. If you think of that in a cropland sense, it's precipitation and whatever fertilizer we want to put on in addition to that inherent soil fertility. If we're on irrigated ground, then that precipitation is augmented by irrigation water and fertilizer. But it's pretty much down to how much water and how much fertility is available to drive plant growth that forms those inputs. Respiration, on the other hand, is the output. That's controlled by temperature and moisture. If it's hot and moist, you're going to lose a lot because those microorganisms that digest that carbon via the process of respiration and lose that to the atmosphere, as long as there's moisture and temperature for growth, you're going to have those bugs consuming that material and releasing it to the atmosphere. In general, if the soil profile stays intact, our loss is limited. So we don't expose what's in the soil to the oxygen in the atmosphere and initiate those chemical reactions, then in general, that carbon will stay in the soil. Extreme overgrazing. And when I say extreme overgrazing, I mean the kind of overgrazing where we have soil loss, long-term degradation, wind and water erosion actually results in carbon loss. And that in itself requires substantial effort and time to restore that capacity. So that restoration part of it is very important, and the numbers can be pretty big, but it takes time and it's costly to carry out that respiration. So in general, if we graze a piece of rangeland, we really don't have that much of an effect on the soil carbon as long as those those rates of grazing are within what is kind of economically viable for managing land. Obviously, if we overstock, we'll eventually lose carbon, but that requires overstocking to the point that animals don't perform and it's not really economically viable to do it. And then finally, and importantly, weather can override management. If you look at those driving factors, we're at the mercy of the climate. Okay, what practices do we use to manage rangeland? Stocking rate. Always stocking rate. That's why we know a lot about it. That's why that first figure I showed, uncertainty, that's where we have our best understanding of how these rangeland ecosystems function, is the relationship between stocking rate and forage consumed. We manage distribution to get good distribution, avoid spot overgrazing and the degradation that comes with that. We know that we can manage season of use to actually change species composition and extend the length of the growing season to take advantage of precipitation and moisture when it's available. And then finally, drought response to avoid degradation and allow for that recovery before it becomes restoration. Now, from a big standpoint, we don't really think that most of our rangeland, and this is privately owned rangeland in the United States, we don't really think that our rangelands are badly degraded from a carbon standpoint. The National Resource Inventory is the best tool that we have for assessing condition of cropland or rangeland or forest or anything like that. They really don't indicate that much of the private rangeland is degraded from a carbon standpoint. Based on rangeland health attributes of biotic integrity, soil stability, and hydrologic function. So for those areas in the green, there are none of those areas that show a loss of the integrity, the stability, or the function for those three factors. The yellow areas are areas that have 10% of the acreage or less. So we really don't have that much rangeland that has lost sufficient cover, had sufficient erosion, or been degraded to the point that we've actually started losing carbon. Now, what that means is that if we haven't lost that carbon from our reference conditions, that carbon is still in the soil, and it's going to be difficult to actually increase that soil carbon through management. Now, moving this into a market framework, how do we turn that land-based carbon sequestration or ecosystem service into a commodity via these ecosystem service markets? We have three things that we need to know: crediting rates, and that how much is there, and what's the risk associated with those estimates; the management protocols, what do we need to do to actually get things to change; and then finally the verification protocols. Because this is a commodity that stays in the soil, it's important that we understand and trust our verification protocols. We have to, as sellers, we have to prove it to buyers. And most of what I'm going to talk about in the next minute or two is from the Chicago Climate Exchange, where we confronted a lot of these challenges in building that system. So what we came up with was largely a default approach. For crediting rates, how much is there? They had to be transparent. They had to be consistent. They had to be accurate. And notice I didn't say precise. We wanted them to be accurate at a regional level. We had to use existing information, and they had to be cost effective. Most importantly, cost effective, because this was a very limited trial in terms of the length of time that it ran, as well as in terms of the opportunities for participation. So we had to meet all of these things without a lot of time to get ready. We couldn't go to the field and do new work. We just had to take what we already knew and turn it into some crediting rates. Our management protocols, just like I showed in the previous couple of slides, were based on two primary factors: grazing management, and that is getting the stocking rate right and getting the distribution right. And then finally in management, on drought response. When we had a drought, we cut those stocking rates back to save the carbon that was in the soil so that we could quickly return to normal after the drought. And then finally, verification was largely the province of aggregators. And these are independent companies that worked as consultants to verify that those numbers that we came up with were correct, and that the management protocols that we were interested in and that producers signed contracts to actually do were actually happening. And on the upper right-hand corner there in that figure, we just broke it down regionally. We came up with 6 regions of the country. And you'll notice that for the most part, that gray area in the Southwest, we didn't even come up with a number there, because for the length of time that this program was going to run, 5 years, we did not feel that we could make a credible estimate of how carbon would change over 5 years that we could back up with any numbers, and certainly not with any field measurements. So those land resource regions there, B, C, E, F, G, H, assigned to those colors in that map. And then according to improved management, that is in tons per acre per year. So anywhere from generally around 1/10 of a ton to around 2/10 of a ton of carbon per acre per year were assigned to the people, the land that was enrolled in that program. So to sum all of that up, arid lands have a limited capacity to sequester carbon. This is not the first pick of a place to do this. In general, and much to our benefit, carbon sequestration is compatible with good management. We already know how to do good management. There's nothing new in those practices. You know, we've been doing this for almost 100 years now. The measurement, monitoring, and verification have challenges to overcome to support a market, especially on arid rangelands. And then finally, government-backed conservation programs probably have some opportunities that a private sector market would not necessarily have for us, given all of our inherent constraints. And I'm going to stop there and turn it over to Jim